Section 10.4 is going to look at right triangles and function values. Right triangle definitions of trigonometric functions. If we let theta be an acute angle of a right triangle, the 6 trigonometric functions of theta are defined as follows. Sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. Cosecant of theta is hypotenuse over opposite. Secant of theta is hypotenuse over adjacent. And cotangent of theta is adjacent over opposite. Note the acronym SOHCAHTOA, which you probably learned back in geometry, is often used to help remember sine, cosine, and tangent. And then remember that the ratios in the second column, cosecant, secant, and cotangent, are simply the reciprocals of those that are in the first column. The reason that this comes about, as we saw in the previous section, sine was y over r, where this was our y value, this height to a point, and this distance from the origin out to our point was our r. And notice that opposite is the y, and hypotenuse is that r. So essentially that's where these came from, the fact that we could have opposite over hypotenuse and adjacent over hypotenuse. So hopefully this is all a reminder from geometry and algebra 2. We're just going to jump right into an example here. Example number 1, it says to find the sine, cosine, and tangent values for angles U and W in the right triangle below. Angle U here, we're going to find the sine of U, and the sine is opposite. So our opposite side is going to be 16 over the hypotenuse, which is 34. We could simplify that to 8 over 17. The cosine of U is going to be adjacent, so the side that touches it, over our hypotenuse. And that simplifies to 15 over 17. And then tangent of U is opposite over adjacent, 16 over 30, which simplifies to 8 over 15. Then we look at angle W. Angle W is down here. The sine of angle W is opposite is 30 over hypotenuse of 34. That simplifies to 15 over 17. Cosine of W is going to be 16 over 34, adjacent over hypotenuse. Simplifies to 8 over 17. And tangent of W is going to be opposite, which is 30 over adjacent, 16. And it is 15 over 8 if we simplify. Now notice if we look at sine of U is 8 over 17. The cosine of W is also 8 over 17. Sine of W, 15 over 17, is equivalent to the cosine of U, 15 over 17. So notice how sine of U equals to cosine of W, and cosine of U is equal to the sine of W. This occurs since the sum of the angles in a triangle is 180 degrees. And one angle is a right angle. Therefore, angle W plus angle U is going to be equivalent to 90 degrees. And because of this, we have what they call the cofunction identities. Our cofunction identities, the sine of 90 minus any angle theta is always equal to the cosine of theta. The cosine of 90 minus any angle is always equal to the sine of theta. Secant of 90 minus theta is equal to the cosecant of theta. Same with cosecant. And then tangent and cotangent are cofunctions. And you can see that here because those are the two that are related. In example number 2, it says to write each function in terms of its cofunction. So if we have the cosine of 43, well, the cosine of 43 degrees is equivalent to the sine of 90 degrees minus 43 degrees. Therefore, the cosine of 43 degrees is equivalent to the sine of 47 degrees. So those are the cofunctions, or that is our cofunction. Tangent of 62 is equivalent to the cotangent of 90 minus 62. So our cofunction, tangent of 62 degrees, is equivalent to the cotangent of 28 degrees. And last but not least, secant of 25 degrees. Its cofunction is cosecant. So it's equal to cosecant of 90 minus 25. The cofunction secant of 25 is equivalent to the cosecant of 65 degrees. Example number 3 also deals with cofunctions. It wants us to find one solution for this equation. The cosine of theta plus 8 is equal to the sine of 3 theta plus 4. Since these sine and cosine are cofunctions, we know that their angles have to add up to 90. So, as a side note, this equation is true only if the sum of the angles is 90 degrees. Since sine and cosine are cofunctions. So all we have to do is take our angles, add them together, and set them equal to 90. We have theta plus 8 plus 3 theta plus 4 is equal to 90. We combine our like terms. 3 theta and theta gives us 4 theta. 8 and 4 gives us 12. I'm going to subtract 12 from both sides. We have 4 theta is equivalent to 78. And then divide by 4. We find out that theta is equal to 19.5. So that's cofunction identities. Now we're going to talk about special right triangles. So you saw special right triangles in geometry, and you saw special right triangles in algebra 2. Remember, if we have a 45, 45, 90 triangle, we know that the two sides have a length of 1, and our hypotenuse has a length of the square root of 2. That's a standard 45, 45, 90 triangle. And then for a 30, 60, 90, we have the side opposite 30 is always 1. The hypotenuse is always 2. And opposite the 60 is the square root of 3. And that comes from the fact that this happens to be half of an equilateral triangle. So if we have an equilateral triangle and we were to cut it in half, we would have 60 degrees, 60 degrees, and all of our sides have a length of 2. Then this 2 would be chopped into 2 pieces that are equal to 1. And 1 squared plus something squared equals to 2 squared. That something happens to be the square root of 3. And when we get into the unit circle, we deal a lot with these special right triangles. This first example here, example number 4, says to find the 6 trigonometric function values for a 60-degree angle. We always want to give exact values. We're never going to give decimal approximations in trigonometry. We will always give fractions. So the sine of 60 degrees. Well, here 60 sine is opposite over hypotenuse. So our sine of 60 is going to be the square root of 3 divided by 2. Cosine of 60 degrees. Cosine is adjacent over hypotenuse. So it's going to be 1/2. And tangent of 60 degrees is opposite over adjacent. So we have the square root of 3 over 1, which we could just write as the square root of 3. Then to find our other 3, we can just use our reciprocals. So cosecant of 60 degrees is going to be 2 over the square root of 3. We need to rationalize. So we multiply by the square root of 3 over the square root of 3, and we get 2 times the square root of 3, all divided by 3. The secant of 60 degrees is going to be 2. And then the cotangent of 60 degrees will be 1 divided by the square root of 3, which we have to rationalize. So we multiply by the giant 1 of the square root of 3 over the square root of 3. 1 times the square root of 3 leaves us with the square root of 3. The square root of 3 times the square root of 3 is the square root of 9, which happens to be 3. And note, we can't simplify this any further. Even though they're both 3's, this one is inside of a radical, and this one is not. Example number 5 here says to find the 6 trigonometric function values for a 45-degree angle. So the sine of 45 degrees is going to be 1, that's our opposite, over the square root of 2. But we need to rationalize, and we get the square root of 2 over 2. The cosine of 45 degrees, since sine and cosine are cofunctions, this is going to be the same, and also our adjacent and our opposite sides are the same, so it's also the square root of 2 over 2. And then tangent of 45 degrees is opposite, which is 1 over adjacent of 1, so we have 1. The cosecant of 45 degrees is the reciprocal of this. I'm going to use the original so I don't have to rationalize. It's just the square root of 2 over 1, which is the square root of 2. Secant of 45 degrees is the reciprocal of that also. It's the square root of 2. And cotangent of 45, the reciprocal of 1 is just 1. I added another example here. It says to find the missing side lengths. In our first example, part A, we have a 30, 60, 90 triangle. So when we have a 30, 60, 90 triangle, there's a rule that says that the long leg is equal to the short leg times the square root of 3. So what's the long leg? Well, the long leg is the one that's opposite the big angle. So this side here is the long leg. This is the short leg, and then C is our hypotenuse. So we know that our long leg, or 4 times the square root of 3, is equal to our short leg, which is A, times the square root of 3. If we divide both sides by the square root of 3, we find out that A is equal to 4. There's another rule that says that the hypotenuse is equal to 2 times the short leg. Well, our short leg is 4, so therefore C is equal to 2 times 4, or C is equal to 8. And hopefully you remember this from geometry and also algebra 2. For part B, we have a 45, 45, 90 triangle. There's 2 ways to do this. One is that we have a rule that says that the hypotenuse is equal to the leg times the square root of 2. The other way that we could do this is that we could just use Pythagorean theorem, because we know that A and B are equal to each other. So I'm going to actually show you both ways. So we know that A is equal to B. So I'm going to rewrite this as A squared plus A squared is equal to 8 squared. Or 2A squared is equal to 64. If we divide by 2, we get that A squared is equal to 32, and take the square root. We get that A is equal to 4 times the square root of 2. Where did that come from? The square root of 32 happens to be the square root of 16 times the square root of 2. And the square root of 16 is 4. So that's how I got that. Or the other way you could have done this is you could have said, we know that our hypotenuse of 8 is equal to a leg times the square root of 2. And then you could divide both sides by the square root of 2. So A is equal to 8 over the square root of 2. And then you have to rationalize. So A is equal to 8 square root of 2 over 2, which reduces to 4 times the square root of 2. So it's kind of up to you. You decide which way is easiest. But then you also know that B is also 4 times the square root of 2, because both of the legs in a 45, 45, 90 triangle are equal to each other. Now we're going to talk about reference angle relationships. It says, let theta be an angle in standard position. The reference angle for theta is the positive acute angle theta prime formed by the terminal side of theta and the x-axis. The reference angle is always found with reference to the x-axis. So it's always between the terminal side and the x-axis. So we're always going to draw our triangle to the x-axis. So example number 1 says to find the reference angle theta prime for the following. We're going to draw a picture to help us. And our angle theta is negative 175. So this is an angle that starts on the positive x-axis and it rotates clockwise and it ends very close to the negative x-axis. That is our angle theta. And theta prime, which is our reference angle, is this angle in here. It's that distance away from the x-axis. So we want to find out what is that little angle in there. And the way that we do that is we say, okay, how far away from 180 degrees are we? Well, we happen to be 5 degrees away from 180 degrees. Or we could have subtracted negative 175 from negative 180. Part B, we have that theta is 460 degrees. So that's the angle that starts on the positive x-axis. It rotates counterclockwise 1 full rotation and then keeps going another 100 degrees. And so it ends, its terminal side is here in the second quadrant. So that's our theta. Our reference angle is going to be this distance that it ends away from the negative x-axis. That is our theta prime. So we know that we went one time around. So 460 minus 360 leaves us with 100 degrees. So we want to know how far are we away from 180? Well, 180 minus 100 leaves us with 80 degrees. So we are 80 degrees away from 180. So theta prime is going to be 80 degrees. For part C, we have an angle of 240 degrees. So this angle starts on the positive x-axis. It rotates counterclockwise and ends in quadrant number 3. And so we want to know, what is this angle here? The angle between 180 and where our terminal side is. So for this one, we are going to take 240 and we are going to subtract 180 degrees. We want to know how far did we go past 180. 240 minus 180 leaves us with 60 degrees. So therefore, our angle theta, or our reference angle theta prime, is 60 degrees. Here we have that theta is equal to 180 degrees. So that's the angle that starts on the positive x-axis, rotates and ends on the negative x-axis. So that's theta. Whenever we have a quadrantal angle, so in this case, we are actually lying on the x-axis itself, there's no reference angle. So here we have no reference angle. for 90 degrees. Start on the positive x-axis and rotate up to the positive y-axis. This also has no reference angle because it is a quadrantal angle. Negative 300. A negative 300 degree angle is going to start on the positive x-axis. It's going to rotate in the negative direction or the clockwise direction, and it will end in quadrant number 1. And our reference angle is going to be the angle, the distance we are away from that x-axis. We want to know how far do we have to get to that x-axis. If we've gone 300 degrees, that means we have 60 more degrees to go. (140 degrees). Start on the positive x-axis, rotate around, and we end in the second quadrant. We want to know how many degrees are we away from 180, or how many more degrees will it take us to get to 180? And that is our reference angle. And in this case, our reference angle is 40 degrees. And then our last one, 10 degrees. Any reference angle or any angle that is in quadrant number 1, its reference angle is equivalent to itself. So here we have an angle of 10 degrees. And that's also the reference angle. As a note, and what we are kind of moving towards is that reference angles of 30 degrees, 45 degrees, and 60 degrees allow us to find exact values of trig functions for those angles. We can also do it with quadrantal angles. But the reason why reference angles are so important is because if it's 30, 45, or 60, we're going to be able to find that exact value. And now we're going to look at how we evaluate trigonometric functions. When we are evaluating trigonometric functions, you use these steps. So the first step is to find the reference angle, which is what we just did. Then you evaluate the trigonometric function for that reference angle, and then determine the correct sign of the trig function value based on the quadrant that it lies in. So example 4 here has us evaluating some angles. We want to evaluate the sine of 300 degrees. So it might be helpful to draw yourself a picture so you can see what's happening. So here we're talking about the sine of 300 degrees. 300 degrees. That angle starts on the positive x-axis. It rotates around counterclockwise and ends in quadrant number 4. And it has a reference angle of 60 degrees. So the reference angle that has been created in this is 60 degrees. And we form a little triangle here. I'm actually going to make that triangle bigger so we can see what we are dealing with here. So this angle is 60, 30. From our special right triangles, we know that opposite the 30 is a side length of 1. Opposite 60 is a side length of the square root of 3. And our hypotenuse is 2. This then allows us to find the sine. The sine of 300 degrees is going to be the sine, or equivalent to the sine of this 60-degree reference angle. So sine is opposite over hypotenuse. It's going to be the square root of 3 divided by 2. Then we have to think, okay, since sine is opposite, where sine is the y value, y over r, our y values are negative, or sine is negative in quadrant number 3. So therefore, we know that this has to be negative square root of 3 over 2. Part B, we have the secant 150 degrees. So if we draw our picture, it will help us to see what's happening here. So this angle starts on the positive x-axis. It rotates in a counterclockwise direction and it ends in quadrant number 2. And we need to figure out what that reference angle is going to be. So the reference angle, how much farther we have to get to 180 degrees, is 30 degrees. We can visualize our triangle here. So we're thinking about this triangle that has a reference angle down here of 30 degrees. And so therefore, opposite of the 30 is a side length of 1. The hypotenuse is 2. Opposite 60 is the square root of 3. This is our reference angle down here. It's the one that we are focusing on. And we want to find secant of 150 degrees. Secant is related to cosine. So therefore, it's going to be the hypotenuse divided by the adjacent, or 2 divided by the square root of 3. And then we are going to need to rationalize. So we have to multiply by the square root of 3 over the square root of 3. And we end up with secant of 150 degrees is equal to 2 times the square root of 3 divided by 3. Cosine of negative 225 degrees. Our angle is going to start on the positive x-axis, and then it's going to rotate in the clockwise direction and end in quadrant number 2. And we need to figure out how far did it go past 180. Well, this reference angle here happens to be 45 degrees, since 225 minus 180 gives you 45 degrees. So if we imagine our triangle in here, this 45, 45, 90 triangle, our legs are going to both be 1 and then our hypotenuse is the square root of 2. So the cosine of negative 225 degrees is going to be adjacent over hypotenuse, which is 1 over the square root of 2. So we need to rationalize. Therefore, the cosine of negative 225 degrees is going to be the square root of 2 over 2. And then we have to decide, is it going to be positive or is it going to be negative? In quadrant number 2, cosine is going to be negative. Therefore, we need to make it negative. And then secant of 180 degrees. This is a quadrantal angle. So therefore, all we have to use is an XY pair because there is no reference angle or special right triangle here. So we pick our point, negative 1, 0, and therefore secant of 180 degrees is equal to r. Our r here is 1 divided by secant is related to cosine, so over x. X is negative 1. So the secant of 180 degrees is equivalent to negative 1. Example number 5 says to evaluate the cosine of negative 225 plus 2 sine squared of 300 degrees. We found the cosine of 225. That was part C in example number 4. We know that it is negative square root of 2 over 2. The cosine of negative 225 is negative square root of 2 over 2. We also found the sine of 300. The sine of 300 was part A. It's negative square root of 3 over 2. The sine 300 degrees is negative square root of 3 over 2. All we have to do is we have to substitute those values into our expression. I'm going to replace cosine of 225 with negative square root of 2 over 2. And I'm going to replace sine of 300 with negative square root of 3 over 2. And then simply evaluate. This is going to be negative square root of 2 over 2 plus 2 times. If we square the square root of 3 over 2, it becomes 3/4. And then if we multiply here, we get negative square root of 2 over 2 plus 6 over 4, which reduces to 3/2. And it's going to be equal to 3 minus the square root of 2, all divided by 2. Example number 6. Evaluate the cosine of 780 degrees. Now we are going to be going more than one full rotation. This angle starts on the positive x-axis. It rotates counterclockwise. It goes one time around for 360 degrees. A second time around, we get to 720. And then we have to go another 60 degrees to get to our angle. So the reference angle that's in here is 60 degrees. So we think about this. We have a triangle that has a 60-degree angle and a 30-degree angle. It's a 30, 60, 90 with the sides 1, 2 and the square root of 3. And we just need to find the cosine of this 60-degree angle. Well, cosine is adjacent over hypotenuse. So the cosine of 780 degrees is going to be equal to 1/2. And then we have to decide, is it positive or negative? All things are positive in quadrant number 1, therefore cosine of 780 is equivalent to 1/2. For part B here, the tangent of negative 405 degrees. We're going to start on the positive x-axis, and we're going to rotate in the clockwise direction. One full rotation is 360, and then another 45 degrees gets us to 405. Our reference angle here is 45 degrees. We can draw our triangle, or think about our triangle. It's a 45, 45, 90 triangle. So the sides are 1, 1, and the hypotenuse is the square root of 2. And we need tangent for this. Tangent is going to be opposite over adjacent. The tangent of negative 405 degrees is 1 over 1, which is 1. But we need to decide, is it positive or negative? In quadrant number 4, cosine and secant are positive. Therefore, tangent is negative. So this value is negative 1. Example number 7. Find all values of theta if theta is greater than 0 and theta is less than 360 degrees, and the sine of theta is negative 3/2. So now we're essentially working backwards. So we want any angle where sine is negative square root of 3 over 2. So first off, we have to think about what quadrants is sine negative in. Well, sine happens to be negative in quadrants 3 and in quadrant 4. We know that there's a reference angle in here, and we need to figure out what it is. And once we know what that reference angle is, we will be able to find the angle that starts here on the positive x-axis and rotates and ends here in quadrant number 3, or rotates and ends in quadrant number 4. Since we know it's negative square root of 3 over 2, sine is y over r. Our y value is going to be the square root of 3, and our r value is going to be 2. Well, with a hypotenuse of 2 and one side being 3, this other side happens to be 1. We're looking at a 30, 60, 90 triangle. And what angle in a 30, 60, 90 triangle is opposite the square root of 3? In this case, our reference angle is 60 degrees. We went 60 degrees past 180. So 180 plus 60 gives us 240 degrees. We also ended here in quadrant 4. This angle is 60 degrees away from 360. So 360 minus 60 gives us 300 degrees. Example number 8, it says to find all values of theta if theta is greater than or equal to 0, but less than 360. And our cosine of theta is going to be negative square root of 2 over 2. We have to think, where is cosine negative? Cosine happens to be negative in quadrant number 1, in quadrant number 2 and quadrant number 3. So we know we're going to have an angle here in quadrant 2 and also an angle here in quadrant number 3. Remember that this is the same as -1 over the square root of 2. That's the unrationalized form. That tells us that our hypotenuse is going to be the square root of 2, and our side of our triangle is going to be 1. We have a 45, 45, 90 triangle. So we have our reference angle being 45, and we know that we're stopping with this one. We're rotating and stopping 45 degrees away from 180. 180 minus 45 gives us 135 degrees. And with this one, we are rotating 45 degrees past 180. 180 plus 45 gives us 225 degrees. Interval notation. So sometimes we will see interval notation, so we need to make sure that we understand what it is talking about. So for interval notation, we are going to use brackets if we have less than or equal to or greater than or equal to. And we use parentheses if we have less than or greater than. And then intervals that go on forever. They are going to contain either negative infinity or positive infinity. And we only use brackets, parentheses with an infinity sign. So if we wanted to convert theta's greater than 90 but less than 360. So on the lower end we have 90 and then it goes up to 360. Since it's not equal to 90, we put a parenthesis, and since it's not equal to 360, we put a parenthesis. For part B, we have theta is greater than or equal to 90 and less than or equal to 360. Since it is equal to 90, we put a bracket, and equal to 360, we put a bracket. For C, we're talking about things that are greater than 90. So the smallest it could be is 90, and it goes all the way up to infinity. So we are going to use parentheses on either end, since it's not equal to either of those things. And then the last one, theta has to be smaller than 270. That means anything smaller than it. So all the way down to negative infinity, up to 270. Since it's equal to 270, we put a bracket on one side. And then on the other side where infinity is, we have to put a parenthesis.